Hey guys, I hope you're doing well. I just want to take a little bit of time and talk about strengths of acids and bases. I gave you a section to read and take notes on earlier, and I've gotten the notes from almost all of you. It was section 16.1, which walked you through the variety of types of acids, your Lewis acid, your Bronsted acids, so on and so forth. For those of you who submitted the answers, it seems like you had a bit of a handle on those, and if not, then we'll spend some time reviewing those. I'll need to know from you guys if that's something that you need me to walk through or you feel like you have it. So let's take a little bit of time and let's talk about strengths of acids and bases. First of all, when we talk about strengths of acids and bases, it's really helpful to think about the dissociation, which means the coming apart of the acid, and how it happens so that we have some type of equilibrium reached. What you have to think about and you have to realize is when you have this acid with water, when you're putting it into solution, basically the acid is working with two bases. One of the bases is that water. The water actually acts as a base. Remember, it's a polar molecule, but it can have the tendency to be a base. Water can have the tendency to be an acid or a base depending upon how it behaves. Usually in acid-base reactions, water serves the purpose of acting as one of the bases. Then you also have, when you look at your acid, you have the non-hydrogen component of the acid that can act as a base. Basically, it's a competition between those two things to see, which is the stronger base? Which one's going to be better at getting the protons donated to them? Basically, they're competing for the protons. They're competing for those hydrogen ions, or actually, we'll just leave it at that. They're competing for those hydrogen ions. So both water and whatever that non-hydrogen base is, they both want those hydrogen protons donated. The stronger one is the one that will win out. So if I look at this particular reaction, I just made up an acid. I've got HX as my acid. There's my hydrogen. This represents some other ion, non-metal. It's in aqueous solution, which means it's in with water. When this HX is in water in solution, it dissociates, and I end up with H3O plus my X minus. I know this is a minus charge because my hydrogen, when it's in combination like this, I know it has a 1 plus charge. So when I look at this a little further, I know this is my acid. Obviously, I know water, and in this case, if this is an acid-base reaction, that tells me, my hydrogen's here. I know this has to be acting as a base. When it dissociates in water, lots of times you're going to see, or you're going to read, like up here, we talk about H pluses. So sometimes it'll be written as H plus if it's in a picture, or if somebody's talking about it, but truly what happens is that free proton hooks up with the water, and I end up with this H3O plus, which is then acts as an acid, and that's actually called the hydronium ion. And then my X minus, whatever that anion is, whatever non-metal it is, with that negative charge, acts as a base. Because my water was the stronger base, it picked up that proton. So I have to think about it this way. If my water is the stronger base, then really I can say, and you might be asked a question like this, in that particular reaction, the water is the stronger proton acceptor. Much stronger than that anion that dissociates from the hydrogen. So the water is what gets the proton. Walking through it kind of again. The water is what gets the proton. We end up with H3O plus. That's basically just H2O plus my hydrogen proton, which gives me hydronium. So it ends up looking like that in solution. H3O plus, and this actually should be an X here, plus my X minus in solution. If the X minus were stronger than the water, then we have to look at it the other way. In that case, the water is not going to pick up the proton. My X minus ion, my anion, is going to pick up the proton. So I end up with water plus HX in both cases. Up here, when I see this reaction, is generally indicating that I started with a strong acid because I've got dissociation. If I see products from a reaction that looks like this, it's usually telling me that whatever acid I started with, that was a pretty weak acid. It didn't dissociate well at all. It doesn't really want to come apart in water. Not a very strong electrolyte. I mean, there may be a few of these floating around individually in water, but it's really not a very strong electrolyte. It's not going to be a very strong acid when it dissociates very little at all. So when I look at these things, and if you see them in a diagram, let's say they're in a beaker. If I have a strong acid, strong base, I'm going to end up with those protons being donated. P pluses are going to be donated to the water. So I'm going to end up in solution with hydronium ions floating around. Of course, I'll still have some water left. And also, because we have dissociation going on here, I'm also going to end up with some of my X minuses freely roaming about. So this is really what I would call an electrolytic solution due to strong dissociation. So in this case, I don't know why I keep writing A, my X is my stronger base. So water is the stronger base, ends up looking like that when I've got X, my X from above as the stronger base. I'm going to end up with that X getting the proton that's donated, or getting that hydrogen. So I end up with HX floating around in solution with my water. So we don't see real strong dissociation. It just shows us what happens if my X anion is a strong base versus my water being a strong base. And we'll look at that a little more thoroughly later on when we start doing some math with it. Okay, so it's really important to remember when you're looking at this stuff, when you're starting with equal concentrations of reactants and products, and when I say concentrations, I'm talking about molarity. When I have equal concentrations, equal molarities, then my proton is always transferred to the stronger base. Always happens that way. That means that the direction of the reaction to reach equilibrium is a proton transfer from a stronger acid to a stronger base, and I end up with a weaker acid and a weaker base. Or think of this as strong acid plus strong base gives me weak acid plus a weaker base. Makes sense. I start strong. When they dissociate, they become weaker. Even though they're electrolytes, they become weaker because they're not bonded as an acid any longer. When I look at this, and I look at, oh my gosh, there's so many different kinds of acids. I know that different acids differ in their ability to donate protons. So if I have a strong acid, then I have one, as we've said before, that almost completely dissociates in water. A strong acid is the equivalent of a strong electrolyte. We looked at that before when we talked about when we did electrochemistry, and even when we worked with batteries and we looked at the acids and how strong acids were actually capable of conducting electricity. So if I have a strong acid, I have almost 100%, and I just wrote D for dissociation. So if you're looking at a picture and it shows that acid really coming apart, a lot of hydronium ions present, a lot of anions present in solution, dissociated though, then I know I've got a strong acid. Very little of the whole acid intact, still bonded, left behind. The solution becomes almost, like I just said verbally, almost entirely hydronium. And in this case, we've been working with the X, with our X anion, and there would be very little of the HX left. So you're not going to see that floating around. If you were actually having a model of it, you'd just see your H3O plus and your X minus. Now, let's look just a little bit at some typical strong acids and what their conjugate bases would be. So basically, I get my conjugate base by removing my hydrogen. And these typical strong acids are ones that we've had before. We've been talking about acids and bases on and off all year. You should have had them in Chem 1. There were some of the ones that I made you remember. If I look at them, perchloric acid, there's my acid, there's my H, my conjugate base. For it to dissociate, what would be floating around in the water or in the solution would be that ClO4 minus. I can do the same thing with hydrochloric acid. It's a very strong acid. It's going to dissociate in water, and it's going to give me some chloride ions floating around with some hydronium ions. And I can move on down the line. All of those group 17 elements that normally form acids like bromine, iodine, with the exception of fluorine, that's not a strong acid. The rest of them are. So what happens is my H dissociates, I end up with hydronium, and whatever I'm left with as my anion becomes my weak conjugate base. I can even look at sulfuric, then I have my SO4 2 minus. When I look at those weak conjugate bases, they really have a very low likelihood of combining with protons because they're weak. They're very weak. They're a much weaker base, or they act as a much weaker base than that water that they're in solution with. So they don't pick up the protons. The water does, forming hydronium ions. So it's really important that you remember your strong acids so that you can pick them out in an equation and you know what's going to happen on the other side of the equation when you look at your reactants versus your products. If I look at weak acids, then I have to talk about it a little bit differently. A weak acid only partially dissociates in water. So a weak acid is the equivalent of a weak electrolyte. My plan with this stuff at school was to do some lab where we actually used some electricity and tested for current to see what type of an electrolyte we had present. But obviously we're not at school, so we're not going to be doing that right now. So weak acid is a weak electrolyte. Only a small portion of that weak acid actually transfers any of the protons in water. So it really pretty much stays together. You'll have a small bit of proton transfer, but not very much. If I have a solution, it's going to look like mostly I'm still going to have my acid undissociated. I'll have a very small amount of my H3O plus and a very small amount of my X minus. But the bulk of it is still going to be that weak acid that did not dissociate. When I look at typical weak acids, there are 3 of them that pop up all the time. Nitrous acid, hydrofluoric acid. There's the one that I said before was not a strong acid. It's one of the halogens that actually doesn't form a strong acid. Hydrofluoric acid, acetic acid. Acetic acid, remember, that's just vinegar, only it's much more potent than the vinegar that we buy at the grocery store. That's been diluted quite a bit. If I'm dealing with a very, very weak acid, they have practically no tendency at all to transfer protons to water. Kind of weird to think about them this way, and I'm not going to get too in depth yet, but each of the things that I have listed here can act as a very weak acid. When I have these very weak acids and I look at them, then my acid dissociation equilibrium lies almost completely to the left. And when I say lies to the left, that means it's on the reactant side of the equation. If it says it lies to the right, then it means it's on the product side of the equation. In a strong acid versus a weak acid, the weak acid dissociation is almost completely on the left. It means they're almost equal. It doesn't really dissociate at all. Versus a strong acid, which it dissociates and it moves equilibrium towards the right of the equation. If I have very weak acids, then I'm going to have some strong conjugate bases, and that's what we're going to start with next time. Be sure that you have taken your notes, spend some time with them, make sure that they make sense. I'm going to pick up from here on your notes that you will actually take on Friday after our meeting. Please reach out to me if you have questions about what I've assigned in the book. Let me know what we need to go over at the start of our meeting on Friday. And also, let me know if you feel like you need me to spend some time talking about the different types of acids and how those things all work. The things that I had you read about and take some notes about in section 16.1. Thanks. Have a good day.